Hello, today I will present our work, Discriminative Class Tokens for Text-to-Image Diffusion Models. I'm Idan Schwartz, and the work is done with Vasti, Nila, Serge, Lior, and Sagi. So in this work, we fix two issues that we can find with text-to-image model. One of them is text ambiguity. Let's say we want a photo of a tiger cat. The tiger here means a type of a house cat, or the same thing can be seen when we are using the word iron, and it's not clear if we want the clothes iron. Another issue with text-to-image is that they really fail to generate fine-grained details when we are using a specific type of birds or any other kind of specific classes. So what is our solution? So we suggest to have a class token. This kind of token represents a class. Then it means there is no ambiguity because the class can only represent clothes iron, or it represents the type of cat. And this is also good for fine details because then the class token can represent a type of bird, and it can then pick on those small discriminative details like the chin color. So how we do that? So it's very intuitive. We generate an image, ask the classifier if the class is correct, and then use the signal from a classifier to update the embedding of the token. We repeat this step, this process again and again. Each time we ask the classifier if this is the correct class or not, until we are getting to a situation where the class is correct, and then we stop our training. In practice, we did it for a batch of images. You can find more details in the paper. Another important issue is that you can't really backpropagate the gradients from the classifier through the entire diffusion process. We only backpropagate to the less denoising step, but it still works. And again, you can find more details in the paper. So some questions you may ask is why not using class condition diffusion models? So we find that class condition models, because they are trained on supervised datasets, have very poor quality compared to text-to-image models. And with our model, you kind of get the benefit of both worlds because you still can get, as you can see in the last row, very high quality and the class is deprecated very accurately. Also, with class condition, obviously you can't use the free-form text, and with our model you can do that, which is another benefit to use our method. Another question is why you can't use textual inversion. So in textual inversion, one can take a few images to learn a concept. Let's say you can take a few images from the class. And what we find that textual inversion is very quickly learned biases on the concept. Let's say that the concept that we are trying to learn only have black and white coloring, or that the background of the concept must be a road. And with our method, it only changes the objects and it's less prone to those kind of biases. Another cool use case of our method is to inverse the action of a classifier in a way to see how a classifier thinks a class looks like. For instance, we find that for American lobster, the classifier thinks that lobster should be presented on plates, which is a known bias. So for quantitative results, we measure accuracy. We measure how accurate the image is generated based on different type of classifiers. And we find that we constantly improve the results using our method. Another way to assess our method is to use the images we generate for augmentation. We take a very small number of images and we add more generated images per class and then train on this augmented data. And we see that our results are much better than using the original stable diffusion. And obviously there are many more examples in the paper about fine-grained classes, celeb faces attributes, and many more. Please check the paper. Thank you.